just a house cleaning thing. You can see this is 8.3. Yesterday we did 8.1. So yes, we are skipping 8.2. That won't be covered. So we'll go straight through 8.2 to 8.6, and that'll be what we cover in this chapter. The layout of these notes is not super user friendly because like all the information or a lot of the information you'll need to answer the questions on the back are just like you can see that the front side is totally informational. If you're okay with flipping back and forth, that's fine. If you don't want to do that, you could you know, be on your Chromebook and kind of have them pulled up there too. I don't know if you want to do all that, but that would be an option. But anyways, this is 8.3, and it's about rational functions and their graphs. We looked at this just a little bit yesterday on, I think it was example 3, where we graphed that function 48 over x. It kind of looked like what you see there on your screen. You know, this graph, it looks similar to that, and then we had a couple branches, right? And so you'll know a rational function when you see it because it has a variable in the denominator. Okay, so our overall learning target is that I can graph rational functions and state its asymptotes, poles, intercepts, domain, and range. So lots going on there. So I'm not going to spend a whole lot of time reading this front side. We'll just flip back to it as we need it. All right. That said, let's go ahead and flip over to the back side. All right, so our first example, and you know, these examples up here at the top are more like what you're going to see on Math Excel. They're kind of just drilling those individual skills. All right, so our first individual skill is given a rational function, are we able to find a vertical asymptote? All right, so let's go ahead and see what it says on the other side about vertical asymptotes. Okay, so there it is highlighted right here. It says f of x has vertical asymptote wherever b of x, which they're referring to the denominator there, is equal to 0. So, you know, we're used to that. You know, the denominator can't be 0. So if we ever see a variable in the denominator, then we think restriction. So that also goes along with our vertical asymptote. So if you see this, your thought is we look here. We just use the zero product property to come up with, sorry, set it equal to 0, to come up with x equals -4. All right. So we'll talk more about what that means, but for now, that's just how you find it algebraically. Okay. All right, so moving on to the next one. Okay, so the next one is similar, but with an addition. Here we're finding the vertical asymptotes and the holes. Okay, so they do use some different language on Math Excel, and I butcher this word, I'm sorry, but you'll probably know it when you see it. On Math Excel, they say, are there any points of discontinuity? I know that's not how you say it, but they're talking about vertical asymptotes there. And then if they say removable points of discontinuity, they're talking about holes. Okay, so so maybe that'll jog your memory when you see that problem. All right, so before we get into either one, we need to first reduce this down. All right, because x over 2 and x over 2 kind of cancel each other out. So really, you know, this rational function is equivalent to, at the end of the day, x plus 2 over x plus 3. And you can keep that in parentheses, but you don't really have to have parentheses, you know, if you just have, you know, a single binomial over a single binomial. Okay. So algebraically then, vertical asymptote. Really, all you look for there is you look at the simplified fraction. So we still look at the we look there, okay, And that's going to give me that I have a vertical asymptote at x equals -3. But not x equals 2. Okay, yes. Yes.
How did you get that and then the one before that when you're speaking the -4 over the?
Because I did the other one wrong. That's why. So you're helping my video right now. Yeah. So on the top one, we should have gotten x equals 4. So yeah, thank you, Madison, for that. Appreciate that. Yeah, because we'd add 4 to both sides. So thank you for pointing that out. Yeah. So our asymptote up top there should be x equals 4. Okay. So appreciate that. Okay. So then for the whole, or as they'll call it on MathXL, the removable point of discontinuity, you look at the original unreduced one. Okay. So you go look here at x minus 2. You do the same thing there. You use the zero product property to come up with, we have a whole at x equals 2. So let's kind of take a second, and you can try to keep up with me here if you want, or it might be okay just to watch in this case. Let's go ahead and look at a couple things that happen on this example. Okay. So I'm going to go ahead and type this in both ways. So the original way was x plus 2 times x minus 2. Let me make that a little simpler by multiplying that out. That would be x squared minus 4. X squared minus 4. That's just going to save me some typing. And then our other one would be x squared plus x minus 6, if I multiplied it out, right? All right, so that'd be the unreduced way, and then the reduced way, we're saying yes. Yeah, if it's like an emergency, you can go ahead and go. You can just keep it. Thank you. So the other one is x plus 2. Do what? Yeah, I'll give them to you here in just a second. Over x plus 3. All right, so let's go ahead and let me fix that. And look at the graph. And that doesn't really show us everything we need to see, but it does, what we can clearly see is that there does appear to be an asymptote at x equals -3. Remember what an asymptote is? That's an imaginary line that our graph gets closer to but never touches. Okay, so you can kind of see that. You know, if we zoomed way out, they would just never cross. You know, and touch each other. They would get closer and closer but never touch. Okay. What we can't see is the hole, though. Okay, I'm not sure if it shows you the hole visually on Desmos. It might. It just shows up as like a circle. Okay. But here's where we can see it, okay? So let me look at the table now. All right, so if you look at, ignore the 2 for now and look at the inputs for 3 through 8, and you notice the outputs are the exact same, right? So that tells me that that we've reduced it correctly, that those fractions are equal to each other, okay? We can also see there when we look at where x equals 2, we can see that on the unreduced version, we do have an error at x equals 2, right? That would be our hole. And you can't see it. You can't see it on the graph, but you can see it within the numbers. And if we went back to x equals -3, we would see an error for both of them. So that's the difference on the asymptote. Okay. Anyways, just wanted to show you that. All right. Now, the hardest thing to figure out or get used to is the next example. Okay. Well, any questions about what we've talked about so far before I move on? All right, so and when we're talking about horizontal asymptote or asymptotes, actually I think there can be only one. This is tougher to remember. Let's look at y. So let's flip over, see what it says about horizontal asymptotes. So that's right there, and notice it has, it doesn't just have one case. It's got 1, 2, 3 possible outcomes. So each of them start with if the degree of da-da-da, right? So we're looking at degree of the numerator, degree of the denominator. Okay, so remember what degree is. Like a quadratic is second degree, a linear is first degree, a cubic is third degree, right? So it has to do with the exponent of your lead term. All right, so if we look back at our example, we have a second degree expression. That's a of x over a first degree expression. That's what they call b of x, right? So the degree of our numerator, or a of x, is greater than the degree of our denominator. So that's this top case. The degree of a of x is greater than the degree of b of x. It says there is no horizontal asymptote, okay? So for this one, we would say none, because the degree of the top is larger than the degree of the bottom, okay? All right, so I'm going to have you guys try the next one. You'll have to reference the table because we have a different scenario there. Looks like we have a first degree over a first degree. So try to find any horizontal asymptotes if there are any, right? If it can be found. All right, I'll just go volunteer here. Anybody think they were able to find an asymptote? There is one. I'll give you a clue there. Yes, it is 2/3. Very good. All right, so this is a case where we have a first degree over a first degree, so they're equal. And if you look at the case where they're equal, it basically says the lead coefficient of the top over the lead coefficient of the bottom. Okay, so we're looking at the 2 and the 3 to come up with y equals 2 over 3. Now, let's look at what that looks like visually. So I went ahead and typed this in while you guys were working. So just looking at the graph. And it's hard to see, right? Because, you know, I could zoom in and get a better picture. But you can see that there is some, there appears to be a horizontal asymptote. And it looks feasible that it could be y equals 2/3. Okay. You know, it looks like there's also, you know, a vertical one, but we're not talking about that here. All right. Does that kind of make sense so far? Let me just zoom in a little bit too, so we can get a little bit of a better picture. So let me zoom in on my y-axis. Let's look just between 0 and 1. So they're still kind of tough to see, but you can see a little bit better that you know, it doesn't look like, you know, 2/3 would be about 2/3 of the way up my vertical axis there, right? It doesn't look like those are gonna cross that. Okay, does that kind of make sense? Does anybody have any questions? And if I wanted to, I could zoom way out, like make my x-axis like negative 10,000 to positive 10,000, and they would never go over that line. Okay. All right. So let's go ahead and try to put all this together by doing a couple of these graphs. Okay. We're going to try to actually fully graph, showing specific details, a couple of rational functions. I don't think we'll be able to finish all three, but that's okay. All right, so it says at the beginning on the front, when you're doing this, you should always factor these out just to see, if you can reduce or anything. So we can factor out that top part to rewrite it as 4 times the quantity x minus 3. But that doesn't really change anything, right? Because we don't get an x minus 1, so, but it's good to check, okay? All right, so your domain, this would be like you could do this at the beginning. We did this on 8.1 notes. If we had a variable in the denominator, we'd go ahead and list any restrictions. We'd say, all right, x can't be 1 because if I plug in 1, I'm going to have a 0 denominator, right? So my domain would be any real number except for my restriction. So instead of having to write that out, I'll just allow you to write x can't be 1. We'll assume that that means all real numbers except x equals 1, okay? All right, so my vertical asymptote goes right along with that, okay? My vertical asymptote is x equals 1. Anybody who's kind of catching on, explain why there is not a hole on this one? Anybody easily explain why the answer here is none for holes? Yes. Yeah, we'd have to have a cancellation. Very good. Yes, there was no cancellation at the beginning, so there is no hole in the graph. Okay. Horizontal asymptote, a little bit tougher, right? But we just did this one. We have a first degree over a first degree. So we would get y equals, anybody see it? 4, very good. So 4 over 1, which just gives us, y equals 4. So I'm getting a little bit ahead of myself. Let's go ahead and draw out our asymptotes. All right. So asymptotes are going to show up on your graph as a dotted line, an imaginary dotted line. So x equals 1 is going to be this vertical line right here. Actually, let me zoom in a little bit while I graph. I think that might make life a little bit easier. So yeah, just tracing this grid line. So I like to make a dotted line and then kind of label it. And then we said our horizontal asymptote was y equals 4. So it's going to be this guy right here. And these are just kind of our guideposts. Okay. All right. Now, x and y intercepts. We could just punch it into our graphing calculator and look for it that way. Algebraically, though, here's how it would look. All right. The x-intercept is the x value where y equals 0. Okay. So if I take my original, zoom back out. If I take my original function rule, 4x minus 12 over x minus 1, and plug 0 in for y, let's see what that looks like. All right, now that looks a little bit complicated, but what happens is you would just, if we're trying to solve for x, we'd multiply both sides by x minus 1, which really just gives me 0 equals 4 times x minus 3. And then we can easily solve for x there, or use the 0 product property and come up with pretty quickly x equals 3. Okay, so that's the point 3, 0. So I'm going to go ahead and put that on there. Like I said, we could see that graphically if we just punched it in, but that's how you do it algebraically. And then our y-intercept would be you'd plug in 0 for x. So that would give me y equals 4 times 0 minus 3 over 0 minus 1, which gives me negative 12 over negative 1, which gives me 12. That one's easy because it always ends up, if you plug in 0 for x, you always end up with constant over constant, all right? So negative 12 over negative 1 gives me 12. So we also know algebraically that this goes through 0, 12, which is up there just off your graph. Let me do that in a different color. So 0, 12 would be like right there-ish, okay? Now, is what we have enough just to go ahead and assume we know what the rest looks like? Probably not. We know that there's probably something up there in the kind of the northwestern part and maybe the southeastern part, but we don't know exactly what it looks like. So there's where we kind of rely on our calculator for the rest. Okay, so let's go ahead and punch it in. So I'm going to do parentheses 4x minus 12. Just to save time. I could do it factored too, but just save a little bit of time. And then over x minus 1, you do need to group that in parentheses for your calculator. Now we can get a visual of what the rest looks like. Okay, so from there we can just use our guideposts and fill in the rest. Okay, so we can see that in the northwest it kind of looks like an exponential growth function, right? So we know that we can cozy up to this asymptote until we start to curve up. We know we pass through that point, and then we're not going to go to the right of the vertical asymptote, so we can get a pretty accurate shot of what it looks like. And then the other one kind of looks like a logarithmic curve, right? So just cozy up to each asymptote and pass through your x-intercept. Then you have a really accurate graph. So you could get a lot of that just by copying your screen, but what you can't exactly see are the asymptotes and stuff. That's why you need to know the algebra. Okay. I'll give you a second to get caught up, and then we'll try to maybe do one more if we have time. Oh yeah, we have time. We're rolling. Anybody have any questions about that one? So again, if this were a test question, I would want to see any asymptotes, any holes. There weren't any holes, but we'll get into how to draw that actually tomorrow, because we won't get to the last example today, I don't think. Okay. All right. So let's go ahead and finish up with this last one, and then we'll get to probably the part C tomorrow. All right. So we want to go ahead and factor. Definitely, if you see a quadratic. So we want to rewrite this as x minus 2 over, does anybody know what that bottom expression factors out to? Minus 3 plus 2, very good. Now, in this case, this doesn't end up helping us, right? Because there is no cancellation, but there could have been, right? We don't really know unless we factor. If we ended up with an x minus 2, then we would have to go a step further, right? But it also does help us with, I guess it does help us with the domain and the asymptote, the vertical asymptote. Okay. So by the zero product property, I have restrictions that x cannot be positive 3 or negative 2. Any other real number would be okay. All right. That represents my vertical asymptotes as well. So we would say x equals 3 is one line. X equals negative 2 would be our other vertical line. So let's go ahead and draw those. Remember, those are dotted lines because that's not actually part of my graph. Just guideposts. So I haven't really seen one with two vertical asymptotes yet, and this one does get a little bit tricky, but that's all right. All right, and again, why do I know the answer is none for the next part? Why do we know there's not a hole, an unseen hole in the graph? Madison? There's no cancellation, right? Yep. So so none there. My horizontal asymptote. So I think this is a case we haven't seen yet. The degree of the top is less than the degree of the bottom. Okay. What's that mean as far as our asymptote goes? Y equals 0, and that it just says that. Okay, there's no reason for that. It just says it. If you look back at the top, or sorry, if you look back at the front, it says if they are equal. Sorry, it is. Wait, did I highlight the wrong one? I do. Yeah, I guess I did. If the degree, okay, it doesn't equal. Yeah, that's why I'm just like, what am I doing here? Okay, sorry. If the degree is less than, then it just says y equals 0. Okay. Now, we are going to see this rule actually end up failing, which I don't have a good reason for why, but I'll try to summarize at the end. Let's go ahead and assume we don't know that right now, and let's draw that out. All right, so got lots of guideposts here. All right, our x-intercept, and we're going to kind of use some generalizations here, but we're plugging in 0 for x. We know we're going to end up with, skip that first step, 0 equals x minus 2, which gives me x equals 2. So we know it goes through 2, 0. Let me do that in a different color. So why is that a problem? Does that point touch our asymptote? Yeah. We're getting tricky with our language here when we're talking about touching our asymptotes. So be easy here. That's why it's one of my favorite math words. You know, it's just so fun to say. All right, but yeah. So then we also have a y-intercept. You guys can't even laugh for that. Come on, killing me. All right, so that's where we're going to plug 0 in for our x's, and we get y equals. And again, just take a shortcut. Instead of showing all of it, we know we're going to get -2 over -6. So 1/3. Okay, so that's a weird point. 0, 1/3. But let's graph it as good as we can. I'm going to zoom. So 0, 1/3 would be like right there, which wouldn't be a problem for our asymptote, but the other one is, okay? So now let's try to see what this thing looks like at the end of the day, right? Because really we get a better picture now that we have all that information when we actually type it in. All right, so we get x minus 2 over, it's easiest to type in the unfactored form, so that's how I'll type it, x squared minus x minus 6. Now you may see that your graph looks really weird, Okay, there is some setting that where your calculator tries to show the asymptotes and it makes it look funky. I can't remember where that is, but if you reset your calculator, it'll fix that. So I can go through that tomorrow. But if yours looks funky, then you know, we'll work on that tomorrow. All right. So can anybody see where, like, which parts of the graph we've already established our rule gets broken. Where does the horizontal asymptote apply? If there's three branches, which two of the three branches does it look like that horizontal asymptote might apply? The left and the right. It gets broken in the middle. Okay. So let's go ahead and fix this then. And again, I don't have a good answer for why this happens here. So really the answer I think would be none. But you can note that it's y equals 0 for the left and right part. We'll call those the left and right branches. Okay. So that rule apparently can be broken. All right, so let's go ahead and try to fill it in, and that'll be how we finish. So looks like we have kind of an just kind of on the left part, you just kind of use your guidepost there. All right, so cozy up to both asymptotes as you go. On the middle, we do have more guideposts, but our rule does get broken. Our asymptote rule does get broken. So I'm going to cross through both intercepts. And then on our last one, it's kind of like the other part. So that gives us a pretty good picture of what it looks like. Okay. Just so you know, does anybody type that in and see like a weird looking picture? Okay. Well, if you happen to, if it looks real weird, like it kind of looks like a heart monitor or something almost. What I would suggest you do in that case is you go to second and then plus to get to memory. Do a reset. I just usually do all RAM. And if you reset it, that should put it back to factory settings and fix it. All right, so here's what I would suggest. I will post the assignment tomorrow, but I'm going to give you some time to work in class. I would highly suggest, even if you don't get to the Math Excel, try to do example C before you come in tomorrow, right? I'll post the notes at the end of the day so you can check them on your own, but we will talk about this example tomorrow in class to kind of lead off. And yeah, so kind of just be ready for that. The one thing we see in that example that we haven't so far is how we would like graph a hole, how that looks like, how you show that on the graph. All right, so virtual kiddos, if you don't have any questions for me, I'll go ahead and dismiss you guys. Feel free to stick around if you have anything. But we'll finish up that last example tomorrow, and we'll have some work time.